Hi guys, welcome back. I want to talk to you today about three things: a voltage regulation, inductances and inductors, and relays. Let's get started. The first idea is the concept of a voltage regulator. You might have run into these before, but the notion is that you have some unregulated voltage that can vary. It can go up and down or whatever. It's not, you don't know it very well. You know that it's greater maybe than a certain minimum, but it could be just about anything above that, within reason. And a voltage regulator's job is to take this unregulated voltage, spend a little of that voltage, and then give you an output that is well regulated. So no matter what the load is, however the load varies, you get the same voltage. So let's get a breadboard here and we'll see how that works. Okay. So this particular regulator is a 7805. It's got an input pin, a ground pin, and an output pin. And basically you put unregulated voltage on the input pin, tie the ground pin to ground, and the output is 5 volts regulated above that. So let's go ahead and do that. So I'll connect this. So this is going to be my quote unregulated supply. It's actually a regulated supply, but I mean I can dial the voltage to whatever I want. So we can see how the output stays fixed. I got to show you the picture. We're going to see how the output stays fixed. Here's the 7805. It's got an input, a ground, and an output. Here's my pretend unregulated supply. I can dial this voltage to anything I like as long as I keep it above a certain minimum. And then the output here is supposed to stay at 5 volts. So let's do that. So I'm going to I'll put the regulator down right here at 567. Let's go ahead and take the unregulated voltage and put it in 5. We'll put ground at 6, and the output's going to be on pin 7 here. Let me grab a resistor to be our load. So that's our resistive load, and we'll connect that guy. Connect that guy to ground. And then I'll just make a ground jumper over on this side. And then we can monitor the voltage. I'll go ahead and put this guy here, and then use this guy to monitor the voltage. Okay, but there's no regulator there right now, so let's go ahead and put the regulator in. The other thing we probably want to do, these regulators work better if you just put a little capacitance across the output to handle those cases where your circuit needs some sudden current. So like if you use a digital logic circuit where it turns on and off quickly, the demands on the power supply are very transient, and so it's nice to have a little extra capacitance there to help provide for that. So let's go ahead and start the thing up. So you can see this power supply is at 14 volts. The meter is at 5 volts, and so no matter what I do with this power supply, now if I bring it too low, it's going to start dropping off. I go below 7 volts or so, there, 7.5 volts, say, it drops off. But if I'm above that, then everything's okay. Now the other thing you have to remember is, depending on how much I've got 10 milliamps being drawn right now, that 10 milliamps times the difference between 14.2 and 5, that's wasted power. So that's the power being dissipated by this voltage regulator. And that's why the voltage regulator has a heatsink, because they do tend to dissipate a lot of power. So you want the unregulated voltage, you want it above the minimum it needs to keep a nice 5 volts. But you don't want to go too far above it, or else you're going to end up dissipating a ton of power in that regulator. Anyway, that's the idea of the regulator. I hope that makes sense. Let's talk a little bit about inductance. So you may remember with capacitance, there was this relationship. I should go ahead and put it there. Q was equal to C times V, right? And that was the basic relationship. That's not what I want. Okay. Q was equal to C times V. If I take the time derivative of both sides, or I divide by delta t, you could say the Q becomes an I and the V becomes the rate of change of V. So the current through a capacitor is the capacitance times the rate at which the voltage is changing. An inductor is sort of the opposite. It's a thing where the voltage drop across the inductor is the inductance times the rate at which the current is changing. So the relationship between voltage and current are flipped, right? So that when the current wants to change, you've got to apply a voltage, or the changing current creates a voltage. It's another way to think about it. In the same way with a capacitor, if you want to change the voltage, you've got to deliver a current because you've got to change the charge on the capacitor. Here, if you want to change the current, you've got to change the voltage. So you've got to provide a voltage to do that. So that's the idea of an inductor. The symbol for an inductor is sort of I can draw it here for you. Let's see if I have a... So if you see an inductor in a schematic diagram, it's going to look something like this. It'll be like a bunch of squiggles like this, okay? And if you have a resistance and an inductor in series, maybe you might see a circuit like this, where you've got a power supply perhaps, and then a series combination of inductance and resistance. When this switch closes, there's going to be no current flowing because you can't change the current through an inductor instantly, because remember, V is di dt, so the current takes voltage to change the current over time. In order to change the current instantly, you'd have to have an infinite voltage. Nobody has that, and so the current can't change instantly. It takes time. It's a rate of change that you get. So anyway, you close the switch, the current starts to build up. The voltage drop across the inductor is L di dt. It's the rate of change of the current. The voltage drop across the resistor, of course, is just I times R. And so, and the sum of those two voltage drops is equal to the voltage of the power supply. That's the way the thing works. So at the beginning, all the voltage drop is in the rate of change of current. And so if you graph the current as a function of time, at the beginning, di dt is positive and the current is 0. So there's no drop across the resistor, but all the drop is across the inductor. But as the resistor gets more and more voltage drop because the current starts to build up, then di dt has to get smaller. So what happens is di dt gets smaller and smaller and smaller, and eventually the current settles down, and it settles down to a value where di dt is now 0. That means the voltage drop across the inductor is 0. All the voltage droppers across the resistor. So obviously this final current has to just be V over R. This initial slope, right, is V over L. So the slope here is V. You can see from the math, this is equal to the voltage drop across the inductor. That's equal to V naught, the voltage of the power supply at the beginning. This is V naught over R. This is, the slope here is V naught over L. And so you can see the slope of this is also the final I divided by this time, the turn-on time. So that means the turn-on time, so the slope, let's see if I can write this out here. It's hard to write with my darn mouse. The slope is V over L. But you can see, just looking at the picture, that's got to be the rise over the run. So that's V over R divided by T. So that means T is V over R divided by V over L. And that means this has to be L over R. Good. That's the time. So the bigger the inductance, the longer it takes, but the smaller the resistance, the longer it takes. A big resistance means it shuts down quickly. A small resistance means it takes a long time to reach equilibrium because it's going to go to a much higher current. One way to think about that. So anyway, that's an inductance. An inductance is like it makes the current it gives the current some inertia. So it behaves like a current inertia. Okay? If you're familiar with inertia. All right. So the last thing I want to discuss is the notion of a relay. A relay, let's look that up. Here's a relay. A relay has, I'll zoom in here a little bit. It's got a coil, which is basically an inductor. It literally is a coil of wire. When you run current through it, it's a magnet. It becomes magnetic, and it mechanically pulls a switch open or closed. Now what we have here, this contact is normally closed. This contact is normally open. If you energize the coil, the contact flips the other way. So this one will be open when you energize the coil. This one will be closed when you energize the coil. So how do I energize the coil? Well, let's just keep it simple. I'll just make a little switch here. And what we can do is take we just got this regulator going here. Let's take the output of the regulator and let's connect this to the coil, and then we'll connect the other end of the coil to ground. So that's going to run, oops, that's not the coil. The coil is here, terminal 5. The switch, and then what we want to do is when we energize the coil, we want to turn on an LED, say. So I'll just get an LED over here. We'll put the anode on one end of the connector and put the cathode to ground. Let's see. Oh, I got to be careful here. Let's so this I also want to go to 5 volts. Okay. Boom. There we go. So the point is, the switch is energizing the coil. This switch is energizing the coil. That coil, when it's energized, you can see the switch is now up. There it's down. There it's up. Let's zoom in here a little bit so you can see it better. I can't move it when the thing's running. When the switch is open, the coil is not energized, and it's normally, this is a normally open side. When I close the switch, it energizes the coil, it closes this switch, and that turns on the LED. So basically, the relay allows you to have a mechanical switch that's electrically switched. But you can run a lot more current through this switch than you can through like a comparator or the output of a 555. The idea is you're taking a small amount of current, running this coil, and that allows you to switch a large amount of current. So this current could be 3 amps. This is a 3 amp relay. You can never get 3 amps out of a 555, but you can get enough current out of a 555 to run this coil. That's the idea. Okay, I hope that wasn't too confusing. We'll talk to you guys next time. So one thing I forgot to mention, and it doesn't show up in Tinkercad, but in real life, if you use a relay, it's a really good idea to put a diode. Just grab a diode here. Now this is not an LED. This is not a light emitting diode. It's just a plain old diode. But the idea is that when you shut that current off, if you go back to, where did my, oh darn it. If I go back to this expression, when you shut that current off, the IDT is very negative, and so it becomes a large negative value, and you get a large negative voltage spike across that coil. And that negative voltage spike can actually go back and damage other parts of your circuit. So what you want to do is to grab your diode and reverse bias it across that coil so that when the coil voltage goes negative, that diode effectively clips that large negative signal. So what I want to do, I'm going to put this end, connect it to ground. This end, I want to connect it to the coil, terminal 5. So I'm going to put it here, bring it over there. It won't have any effect in Tinkercad. It's gonna operate exactly the same way it was operating before. But in real life, it'll help preserve the life of your other electrical components. Like if you've got a comparator or a 555 or something, that'll help out. All right.